Thanks a lot. It's a pleasure to be here. I flew in from Australia recently to come here, and it's a real honor to be with all of you today. And I've enjoyed the thousands of picture-taking opportunities we've had so far. There'll be more to come, I'm sure. In any case, what I want to talk to you about science today. I wanted to the title, which I decided to, I guess I screwed up because we're going to play some music, but the title I think was, if this works now, unless I, there we go. But the title was The Greatest Story Ever Told. We'll let her sing through this because I like this song anyway. Because what I want to talk about is really the greatest story that's ever been told. That's often used for a different book. And I'm glad that Seth showed this. I was after Zach's discussion. If this is working, why is it not working? Interesting. Let's try it again. There we go. I put that up, you know, and I thought, oh, I'll show that because I tweeted it a while ago, and I said, I don't know if this is real. I always suspect, people send me things, and I always am suspicious. I'm skeptical, it turns out. But it is. I checked it out. It really is. But Seth showed it, and I said, that's, for a lot of kids and adults around the world, that's the greatest story ever told. But it's so boring and tedious and wrong that I thought I would spend more time on the real one. And so I want to tell you a story that's unsung, and the story of the Standard Model of particle physics, the greatest intellectual activity and discovery and endeavor that humans have ever taken. And I want to take you through that, and it'll only take a couple of hours, I think. It's better than any man-made myth, and what for me is it's a sublime mix of culture and technology that, as I've often said, that science is not just about technology, it's about culture. It is a very vital part of our culture, and I wish, as Zach was saying, in fact, that it was a more vital part of our culture. It should be, you're not literate if you're scientifically illiterate. And we need to remind people of that. And it also, for me, it validates this wonderful notion that it's all a big accident, and just get over it. So, this is an image from a famous book, The Lion, the Witch, and the Wardrobe, which is basically a religious book. But it nevertheless characterizes this fact that is at the heart of religion, but also all of human activity. And that is that people, we're hardwired to want there to be more than meets the eye. Clearly we're hardwired for that. That's one of the reasons religion has been so prevalent in all civilizations throughout all of human history. We want there to be more there than meets the eye, a hidden universe. And while that's the motivation of religion, it's actually been validated by science. And I want to talk to you about this hidden universe that we have discovered beneath our eye. And in fact, I like this in a way, it's kind of prescient because in Narnia, you all know the story, but you walk into this wardrobe, this professor's wardrobe, and you go into a different world. But that requires an extra dimension, because if you go behind the wardrobe, it's not, that extra world isn't there. So the only way you could actually go in and sit a whole other world is if there were an extra dimension that intersected at one point. And we'll come back to that later. Okay. So I want to start with the modern vision, the modern way of discussing the fact that there's a hidden reality, that what science does is takes the universe of our senses and explains that things that often seem very different are really the same, and really tries to seek what's below the surface. And Plato, who this is, by the way, was big on that. And when I was in school, because I went to school, grew up in Canada, so I got a good education. And so I was forced to read Plato's Republic and in high school. And I've often gone back to it because, in spite of the derogatory remarks I make about philosophy, which I stand by, Plato's cave is a wonderful allegory for modern science. And I went back to my high school book and I looked at the picture from Plato's cave. So Plato's cave, the allegory in the Republic, is this allegory for what he would say the natural philosopher is all about. And that he likened reality to being in a cave and being captives in a cave and seeing the shadows of the real world. The real world's out here, And we live in a world where we're forced to see the shadows of reality. And the job of the natural philosopher is to try and intuit the real world that is at the basis of these shadows. What I like about this is that this was a book from the 1950s. And so you see that these people these are women in bikinis chained to, in Plato's day it would have been little boys actually. But the point is that and he said in the cave that if you actually were released and never went out and saw the real universe and came back and tried to explain it, people would think you're mad because it is so strange. And he had no idea how strange it really was. And I think about this all the time because that's what I do for a living. As in some sense, I'm fortunate enough to be able to try and seek a little bit about of this real world. And it's happened in a lot of different ways. And whenever we do it, as I'll describe, we discover hidden connections between things that we didn't think existed before. So let me give you an example from Plato's cave. So if you were those people in Plato's cave, you would look at those shadows during the day and you would decide that there's no such thing as length. There's no such thing as the length of something which remains the same, because you might see at a certain time of day, say a ruler would look that big, and then another time of day the ruler would look that big. And you'd say, well, okay, all lengths change during the day, and that's just the way it is. But if you were the natural philosopher, you might say, hold on a second. Maybe there really is such a thing as length, but we're only seeing a two-dimensional projection of a three-dimensional reality. So let's say, looking down on this group and then looking at the shadow, so the ruler is this way. We see the light coming from outside, projecting the ruler that way. Let me see if I can... oh, this is from behind. I can't do it. Okay. That's all right. I'll have to use just the diagram. So the ruler's that way, but then, of course, if I rotate the ruler in an extra dimension, the projection of the ruler, the shadow, will get shorter. So the philosopher might say, you know what? In the real world, there really is something that's invariant, something that's length. And the reason that we see lengths change is we're seeing a two-dimensional projection of a three-dimensional world. And so there's something that connects these other, and there's something invariant. There's some fundamental property of nature that I don't get by seeing just the shadows of reality. And we live in a world where many things seem that way, where they're quite different. But we're just seeing the shadows of reality. And that's a story of 20th century physics and 21st century physics that I want to relate to you. And I want to jump from Plato to one of my favorite scientists of the 19th century, this was Michael Faraday. Michael Faraday was the greatest experimental physicist of his day. He had no formal education, and for the school children here, and there are a few, you learn something very important from Michael Faraday, which is always to suck up to your teachers. Okay? Because Faraday was he was actually a bookbinder's apprentice, and he went to the lectures of Humphrey Davies, who was the head of the Royal Institution at the time. And he took very careful and beautiful notes, and he bound them into a beautiful volume and presented Davies with this volume of lecture notes, beautifully bound, and said, "Can I be your assistant?" And Davies said, "Sure." And then Faraday worked his way up and eventually became head of the Royal Institution and discovered, experimentally, the laws that are the basis of our modern civilization, the laws of electricity and magnetism. And he was doing strange things with jumping frogs, and he discovered something quite remarkable about that there was a connection between electricity and magnetism. And this is what made him famous. And in fact, I just wrote a piece which just appeared yesterday, actually, about Zach was talking about the ridiculous legislators in Louisiana and Oklahoma, but of course they're not unique. And Lamar Smith, who's head of the House Science Committee, sent a letter to the National Science Foundation basically saying that they shouldn't fund fundamental research. And he wanted to see different, he wanted to get the justification that certain grants were being approved because he didn't know if they were in the national interest. And this notion that fundamental research is kind of useless and is prevalent in our society today, and it's very scary. But it was true even when Faraday was there. There's probably an apocryphal story, and I've heard various versions of it, where the Prime Minister Gladstone came at the time and said, he looked at this laboratory, these jumping frogs and these coils, and said, you know, what use is all this? And Faraday said, it's so useful that one day you'll tax us for it. And in fact, since electrical power is basically what he discovered, he was right. And so what he discovered was something weird, that electricity, magnetism, you know, when you're a kid, you learn about both with static electricity, and you play with magnets, and they seem the same, but they seem different. And what Faraday showed was that there were different manifestations of the same thing. That one person's magnetism was another person's electricity. It had been long known that if you moved an electric charge, a current, you could produce a magnet. So you could produce magnetic forces with electricity. But people wondered whether magnets would ever move charges, and people for the longest time brought magnets up to charges. And Faraday, in an accident one day, had an electromagnet, and he turned it off and on, and discovered when in the act of turning it off and on, it produced an electric field. And suddenly there was a connection between electricity and magnetism. That was all codified by the greatest theoretical physicist of the time, James Clerk Maxwell. But the thing I wanted to tell you about Faraday, which was interesting, is that he hadn't been schooled and therefore wasn't trained in mathematics. And he argued he'd only written one mathematical equation his entire life. So he tried to understand electricity and magnetism, and he used a mental crutch. He said, I can't do the mathematics, but I get a picture. And this was a problem that Newton had faced earlier. Newton wondered how the Earth knew the sun was there so it could go around it. And he never figured the answer. And he said, well, I frame no hypotheses. I just won't worry about it. But Faraday worried about why one electron would feel a force from another electron. He said, well, I can understand this if I imagine, I just invent this, a field around each electron. So any charged particle, and I'll picture it as by drawing lines going out from every particle. And the number of lines will depend upon how much charge there is. The bigger the charge, the bigger the field. Okay? And then, using that picture, he's able to say, well, for one kind of charge, positive charges, the field lines go out, and for negative charges, the field lines go in. And it turned out that with that picture, he could draw these so-called lines of force, pictorially, which represent exactly, accurately, the mathematics of electromagnetism. He got everything right with this picture, just by this invention of something he called an electric field, which was just a mental crutch for him to understand why. See, when one charge was near another, it was, if this one sets a field up throughout all of space, when I put another charge in there, it feels that field and knows to be repelled or attracted. That was just an invention in his mind. But then came James Clerk Maxwell, who said, okay, well, this is interesting, because what Faraday showed is that if I jiggle an electric charge, I have a changing electric field, and I know it produces a magnetic field. And what Faraday really showed by turning the magnet on and off is if I have a changing magnetic field, this invention, I'll produce a changing electric field. And he said, this is interesting, because that means if I jiggle a charge back and forth, I'll have a continuously changing electric field. It'll produce a continually changing magnetic field, which will produce a continually changing electric field and a magnetic field and an electric field. And there'll be a disturbance that'll propagate throughout space. And I can calculate the speed of that disturbance just by going in a laboratory and measuring the strength of the force between two electric charges, and then going in a laboratory and measuring the strength of the force between two magnets. And just getting those two strengths, I can plug it in, solve the equations, and I can calculate the speed of that disturbance. And he calculated it and discovered the speed of that disturbance was the speed of light, proving that light was actually nothing other than a wave of electric and magnetic fields moving along. So that invention in Faraday's mind, that mental crutch, was real. That thing he just invented because he didn't like doing the mathematics was so real, it's real before your eyes. You couldn't see it without. So that fact that he had captured that hidden reality, that the light that we see is just a wave of electric and magnetic fields, came from the realization that these two very different things, electricity and magnetism, were different manifestations of one force we now call the electromagnetic field. Okay. And then along came this guy. He didn't recognize the other two pictures, but he recognized this one. Everyone recognizes Albert Einstein. Now, I get a lot of letters every single day from people who have new theories of reality. And they want me to learn about them. And they tell me that their friends think they're crazy, but everyone thought Einstein was crazy. It's kind of like a William Lane Craig syllogism. You know, everyone thought Einstein's crazy. I'm crazy, therefore I'm Einstein. And so the problem is a lot of people who are crazy are really crazy. But but what they tell me is, you know, everything is wrong. I've discovered the new theory, and all this stuff that we now think is wrong. And they don't realize that that's not the way science works. Science works precisely the opposite. That which is right, namely that which has satisfied the test of experiment, will always be right. It will always be accurate at some level. And the progress of science, of course, if I take a ball and throw it, it will be described by Newton's laws, and it'll be described by Newton's laws now or a million years if that's the next time my old home team, the Cleveland Indians, win the World Series. And the point is, I may learn new things at the edges of physics, but Newton's laws work. Now, what Einstein did that was profoundly important was not throw out the laws that went before him when he developed relativity. In fact, what he did that was remarkable, he said there are two things that are true. One are Maxwell's laws. Maxwell said, if I shake an electric charge, it will produce a disturbance that will propagate out at the speed of light, and I can calculate that disturbance by measuring the strength of electricity and the strength of magnetism. That's Maxwell. Galileo, a few hundred years earlier, had said, if I'm moving at a constant velocity, I don't know I'm moving. Any of you who've been on trains in Europe, not in the United States where they're crummy, but in Europe, or maybe in a subway station, you know, you're at a station and you see a train next to you and it starts to move, and you don't know if you're moving or they're moving. Because if you're moving at a constant velocity, you can't tell you're moving at all. There's no experiment that can prove that you're moving. You all think you're standing still, but of course we're moving at 30 kilometers per second around the sun. But because we're moving at a roughly constant velocity, there's no way we can do an experiment that'll say that we're not at rest. So moving at a constant velocity and at rest, every physics experiment you do will give the same result. You throw a ball up in an airplane if there's no turbulence when you're walking down the aisle or standing still, and it'll come back down as if you're standing still. Okay? So, got that? Galileo, no experiment that could tell the difference between whether you're moving at a constant velocity or standing still. Einstein said, Maxwell says, jiggle a charge, light goes out at the speed you can measure. Okay, I'm now going to teach you relativity. Okay? Well, we'll see. No, but this is what I hate about the way physics is taught in schools is that people are told a bunch of stuff like it's the Bible. Like, okay, the speed of light is uniform for all observers. We believe that, and we'll pledge allegiance to that this morning. But that's not the way it works. It's not as if Einstein said that and we like it. Okay? Einstein was driven to that, and here's the reason why, okay? And it's not too difficult to understand. Well, you could tell me whether you think it's too difficult to understand. Okay. Einstein said if both these things are right, and they are right because we can measure them experimentally in the laboratory, the problem is they're inconsistent. Both those things are right, but they lead to a paradoxical result when you put them together. For example, the first time I wrote about this, my daughter was very young, so I wrote about it in terms of projectile vomit. So say you're driving in a car with your young daughter, and you're going 30 miles an hour, and she vomits on your head from the back seat at 10 miles an hour. Okay? So it hits your head at 10 miles an hour, but someone on the ground sees you going by, you're going 30 miles an hour, the vomit is moving 10 miles an hour in the car. So relative to them on the ground, the vomit is moving at 40 miles per hour. We okay with that? Okay. If you're not, just forget it now. Okay. Now, okay. Great. But now let's say you have a 21st century kid who's got a laser beam. Okay? So my daughter shoots a laser beam at my head. Okay? Well, so if I'm in the car, I see the light coming at me at the speed of light. Okay? But what will someone on the ground measure? Okay, well, the point is, if common sense was true, then someone on the ground would measure the speed of light plus 30 miles an hour. Just like the vomit, right? But Einstein said that can't be the case because of Maxwell and Galileo. Because, remember, I'm moving in a car at a uniform velocity, so every experiment I do should give me the same result as someone on the ground. But if someone on the ground measures that light ray going at 186,000 miles per hour plus 30 miles per hour, then they're measuring the speed of light to be different than me. But Maxwell told me that if I jiggle a charge, it will move out at a light ray will move out at a speed determined by the strength of electricity and the strength of magnetism. So if the light ray is traveling relative to the person on the ground at a different speed than me, then that person on the ground must measure electricity and magnetism to have a different strength than I will. But Galileo says, no, that can't be the case because you're moving at a constant velocity. So you see, it's impossible for that common sense notion to be true if Galileo's right and Maxwell's right. But they're both right because they satisfied experiment. So what Einstein did that was so remarkable was not to throw out these two things that were inconsistent, but to make them consistent by saying, how do we measure speed? Well, speed is distance traveled over a given time. Therefore, if the observer on the ground must measure the light to have exactly the same speed relative to them that the person in the car does, the person on the ground must measure length and time differently than the person in the car. Now, that was a bold and amazing creative act, but he was driven to it not by throwing out what had worked, but by taking what worked and making it consistent. So he said the only way these two things, which experimentally have been verified, can be consistent is if space and time depend upon the observer, if space and time themselves are relative. Now, as a result of that, three facts happen. First of all, it turns out that turns out that if I take a ruler and I'm running very fast with respect to you, that I'll use an example from earlier. Take a penis, and I was just thinking about you. There we go. The average 5-inch penis. Okay, I can't believe I'm letting you videotape this, but anyway, and it's moving very fast relative to you. Then relative to you, it's going to look like it's 4 inches, okay? It will be 4 inches. Lengths really do contract. Okay. I can't believe it. I don't know what's happening. I was just telling someone last week in Australia TV, I blew up a condom on TV, so I don't know what's happening. But anyway, it turns out events that are simultaneous for one observer are not simultaneous for the other, and the other thing is that time dilates. If I'm moving very fast with respect to you, my clock will be ticking at a slow rate. It's not an illusion, it's true. We measure it every day in physics laboratories around the world, in undergraduate physics laboratories. If I'm moving with respect to you, my clock really is ticking more slowly than yours. These are aspects of the reality that Einstein was forced to by these two results, this hidden reality. But it's more hidden than you thought, because in fact, his one teacher that liked him in school, Minkowski, in 1908 said, what Einstein had done was unified space and time. And he said, henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Because, in fact, I think if I go back, I've got to remember which direction back is. No, well, okay, so now I know which direction back is. Remember that first implication of relativity was, if I'm moving with respect to you, penises are smaller. Okay? Everything is. Well, I prepared your minds for that. This makes it look like length is not invariant. The length of this laser beam will depend on its motion with respect to you. But if I'm the natural philosopher, maybe I would say what's really happening is that in fact, in some sense, this ruler is being rotated. but not in a three-dimensional universe, but in a four-dimensional universe. And in fact, that's what Minkowski showed relativity implies, that space and time together are unified into a four-dimensional reality, and when we look at anything, we see a three-dimensional slice. When I take a picture of this room, or any of you take a picture of me standing from wherever I am, I get the sense that I took a picture at that instant, but that's not true. Because the light from the people at the back of the room left them earlier than the light from the people at the front of the room. So I'm seeing a slice of a four-dimensional continuum of space and time. And the three-dimensional slice I see every instant for me, when I look out at this room, I see a three-dimensional slice of a four-dimensional world. Space plus time. And the slice I see depends upon my motion. And so in space and time, there's something called a space-time length that's invariant. But I see a different version. Part of this ruler, it turns out because the different ends of it are clicking at have different times for you, the ruler's shorter, so it's shorter in space, but it's spread out in time. And so what Einstein really showed was exactly that analogy to Plato, and this is what Hermann Minkowski pointed out, is that what Einstein's relativity tells us is there is an invariant. It's a four-dimensional invariant called space-time length. And we live in a world in which space and time are tied together in a four-dimensional universe that we had no idea of before, the ultimate hidden reality. So now we've had a unification not just to electricity and magnetism, but a unification of space and time. And it goes on. The next unification is the one I want to concentrate on. And it began by a number of other kind of paradoxical results. First of all, between 1950 and 1975, all sorts of strange things that seemed sensible were discovered to be wrong. Or at least more complicated than we thought. When we started to build particle accelerators and smash particles together, what did we discover? Well, up to that point, there were only protons, neutrons, electrons. We smashed them together. What happened? New particles were created. And the more energy we had, the more new particles were created. It looked like there became an infinite number of elementary particles. Maybe there were no particles that were elementary. Maybe something crazy, it amazes me that people believe this in the 1960s, called the bootstrap theory was developed, which said ultimately it was kind of like a Zen physics kind of thing. All particles were made up of all other particles. Think of that, okay? That's what people were driven to by this kind of craziness. The next thing that resulted, which was even crazier, was this realization, look, I can tell the difference between left and right most of the time, although when I drive in Australia and here, I always forget which is the blinker. But because, well, things look different on the left and right. The room is a little bit different here than there, okay? But no one thinks that the laws of physics fundamentally can distinguish between left and right. It's an accident of our existence, right? Because electricity, magnetism, all gravity, they don't tell the difference between left and right. What was discovered was in 1965, in fact. Well, actually, no, 55, sorry. Was that left and right aren't the same. That while two of the four forces, electricity, magnetism, and gravity, can't tell the difference between left and right, there was one force, called the weak force, which could. And when neutrons decay, and I'll get to neutrons, they decay, it turns out they always preferentially decay in a certain direction. The laws of physics do tell the difference between left and right. That was so remarkable that it was proposed in 1955. The experiment was done in 1956. Within a year, the people who proposed it, the two young guys who proposed it, won the Nobel Prize for that discovery because it was so remarkable and flew in the face of everything that we thought was true. It's the only time it's happened that I know of. And the Nobel Prize, by the way, is supposed to be given for the best work that year in science. But it's always given for the best work 40 years earlier. Okay? But that was so remarkable and so unexpected that the laws of nature actually do distinguish left from right, that it was remarkable. Okay. Then, and many of you know I wrote a book about Richard Feynman, a hero of mine and many other people. Feynman showed that, in fact, when you apply the laws of quantum mechanics and relativity, the world is even stranger than you thought. When you put quantum mechanics together with the relativity, which I already showed you how strange it was. But quantum mechanics is much stranger than relativity. Relativity I can explain to you to some of you in a few minutes. Quantum mechanics, nobody understands, okay? It is just crazy in the extreme. But what Feynman showed was that I could understand these laws of electromagnetism that Maxwell and Faraday had developed by saying something strange happens. That what really happens, what really transmit the electric force between two electric charges well, actually, I think I probably have it in animation next. Let me see, yeah. Is that this, well, in this case, an electron and a positron, doesn't matter, but they emit a particle of light which travels a little while and then decays back into an electron and a positron. So if I want to go back to that other example, which I actually think I had here. Yeah, there we go. I'm trying to remember which direction I have. That when when two electrons are repelled, what they're doing is they're exchanging a particle. The particle of light, the quantum of light called a photon. It's called a virtual photon because you can't see it. It's just being exchanged and it's causing that force. And all forces that we feel in quantum mechanics are due to the exchange of particles, virtual particles. Well, that's not too crazy. Except, once you allow for quantum mechanics and relativity, you've got this problem. Because, so here's a particle A moving along, and it exchanges a photon, which causes another particle B to be repelled. The opposite process can happen, where particle B exchanges the particle, emits the photon first. So it doesn't matter which one happens, whether B emits the photon before A or A emits the photon before B, the force occurs. But now, what Feynman showed was that this very fact of virtual particles can be emitted causes a huge problem, which is another paradox. And it's based on something called the Heisenberg uncertainty principle, which says in quantum mechanics, as I often say, as in corporate America and in the White House, if they can't see you do it, anything goes. Okay? Quantum mechanics says that on a scale of time shorter than you can measure it, anything can happen. So, for example, Einstein tells us nothing can travel faster than the speed of light. That's true. You can't measure anything traveling faster than the speed of light. But if you can't measure it, anything goes. Quantum mechanics combined with relativity says if I have an electron moving along, for a little while it can travel faster than light. As long as it does it such a short time, you can't measure it. Okay? So that's allowed in quantum mechanics. But the problem is, Einstein told us if you're traveling faster than light, then you're moving backwards in time. So what it really says is, for an observer, another observer, that electron would look like it's going forward in time and then backward in time and then forward in time again. And Feynman said that must be happening. But how would we see that? Well, what's an electron moving backwards in time look like? Well, if a charge is moving backwards, a negative charge is moving backwards in time, it looks like a positive charge is moving forward in time. So quantum mechanics and relativity imply that there must be particles that have the opposite charge of electrons, the same mass, that look exactly the same. The antiparticles of electrons called positrons. Quantum mechanics and relativity tell us that every particle in nature must have an antiparticle. So this process, instead of looking like this, would look like this, where an electron is moving along, and suddenly out of empty space, an electron-positron pair is created, and the positron annihilates that electron. And so I start out with one electron, I end up with one electron, but for the time in between, I had three particles. And that process must happen. That must mean, as many of you heard me say in a different context, that empty space is a boiling, bubbling brew of virtual particles. Quantum mechanics and relativity tells us that beneath our very eyes, empty space has particles popping in and out of existence on timescales so short I can't measure them. Particles and antiparticles. This is indeed an animation which is based on a calculation. This is what the space inside of a proton looks like. You learned, if you went to a good school, that there are 3 quarks inside of a proton. We lied. Okay, well, there are 3 quarks, but they're not the important stuff. there are also these virtual particles and fields popping in and out of existence, and they're responsible for 90% of the mass of the proton. The quarks only account for 10% of it. Before your very eyes is an empty space, is this incredible universe of virtual particles popping in and out of existence. And of course, as I recently wrote a whole book about the significance of that, because it tells us that in fact everything we see can pop in and out of existence without any supernatural shenanigans because of that. So I'm very proud of this fact. But there's one other fact that will now take us to the modern world. I've taught you relativity, I've taught you what we call quantum field theory, the unification of relativity and quantum mechanics. And then there's this weird fact that the neutron is radioactive. I said neutrons decay. Now this should surprise some of you, because most of the particles in your body are neutrons. The dominant particle in your body is neutrons. Most of the atoms in your body have more neutrons than they have protons. But if I take a neutron, the average neutron will decay in 10 minutes. You will notice, many of you, painfully, this lecture has already gone on for more than 10 minutes. So what gives? A remarkable, I'll use the word miracle in this room, a remarkable fact of nature. So, if I take a neutron, hold it out here, it'll decay in 10 minutes. Why are you still around? Many of you are asking that question. But, well, what happens when I drop a neutron in a nucleus? It gets bound in a nucleus, right? It gets pulled in. It takes energy to pull it out. So it loses energy when it gets bound into the nucleus. But what did Einstein tell us? E equals mc squared. Energy is related to mass. So when the neutron falls into the nucleus, it loses energy and therefore gets a little bit lighter. Then the neutron is just a little bit heavier than the proton. When it's in the nucleus, it's too light to decay. The reason the nuclei in your body are stable and the neutrons in your body are stable is that they've lost just enough energy so they can no longer decay into protons plus electrons plus neutrinos as it would do in real space. And so when I remember I learned this in high school, and I was amazed to discover this fact that it blew me away, that the most particles in my body were radioactive. And it's just an accident of nature that the proton and neutron are so close in mass that decay can't happen in a nucleus because the neutron has lost just enough mass so they can't decay. A remarkable fact of nature. Now, this decay of a neutron was not due to electromagnetism, wasn't due to gravity. That can't produce that kind of decay. So it was realized there must be a new force in nature that's responsible for that decay. Now, because neutrons last so long, 10 minutes may not seem long, but in a particle physics perspective, it's very long. That new force must be very weak. So it was called the weak force. We're so creative. And this is one of my other favorite physicists, Enrico Fermi, who was probably the last great particle physicist who was equally good at experiment and theory. He was involved in the Manhattan Project, building the first nuclear reactor underneath the football field in Chicago, at the University of Chicago, based on the presumption correctly that if you kill a bunch of football players, there's no loss. But anyway, Fermi gave a theory to explain neutron decay, for which he won the Nobel Prize. The first theory of the weak interaction. Now, the point is, it didn't take long for people to say, well, look, if the weak force is due to the exchange of a photon, a neutron is made of 3 quarks, it changes into a proton, emits an electron and a neutrino. Maybe this decay, this weak decay, can be due not to the exchange of a particle of light, but some new elementary particle called the W particle. Now, the weak force is very different from the electromagnetic force. The electromagnetic force is long range. We can experience forces from a charge in Alpha Centauri. The weak force only happens inside of a nucleus. Now, the Heisenberg uncertainty principle tells us why electromagnetism is long range. Because remember, the electric force is conveyed by this particle of light, a virtual particle that is created here and absorbed here. Okay? It's virtual because when it's created, it violates, you know, in principle could have some energy, and suddenly energy isn't conserved. So it has to disappear in a time scale so short you can't measure that violation of energy conservation, the Heisenberg uncertainty principle. But because the photon is massless, because the particle that conveys light is massless, the photon can carry an arbitrarily small amount of energy. And that means it can survive an arbitrarily long time. The photon that conveys the weak force between Alpha Centauri, a particle, and Alpha Centauri here, carries almost no energy, which is why it can travel 4 light years before being absorbed again. Therefore, the weak force, if it's short range, it was argued, must be conveyed by a very massive particle. If it's very massive, then it can't travel very far because it carries a lot of energy and it has to disappear in a time scale so short you can't measure that energy violation. The more massive a virtual particle is, the shorter it can live. So everything held together if the weak force was conveyed by a heavy particle and the photon and the electromagnetic force by a light particle. You may wonder where I'm heading, but it's all going to come together in a second. Now there's a problem. When people tried to calculate, let me go back to this. Let me just keep going back and forth. No. Electromagnetism, the quantum theory of electromagnetism is the best theory in nature. It's called quantum electrodynamics, and we can predict numbers to 9 decimal places. Okay? There's no theory that's better, and compare them with experiment. Okay? When we tried to calculate with this theory, the problem is we came up with infinite answers, infinite predictions which are infinite. Infinity is a problem. Physicists don't like it, but as I pointed out, mathematicians like it. And the reasons physicists don't like it, because you can do strange things with infinity. So I want to give you an example. This is Dennis Hilbert, or David Hilbert, who was the greatest mathematician of his time, and he invented an example to tell you how weird infinity was. It's called Hilbert's Hotel. So say you go to Las Vegas, you go to TAM, and you're in an infinitely big hotel, okay? And you go in and you try and get a room, and the hotel is full. And you say, okay, I'll go somewhere else. The guy says, no, I can fix this. It's full, but no problem. We can find room for you. How is that? Well, let me just draw the hotel as a series room, an infinite number of series. Room number 1, 2, 3, 4, 5, 6. The clerk says it's very simple. I'll just move the person from room number 1 into room number 2, the person from room number 2 into room number 3, room number 3 into room number 4, and keep doing it. And then room number 1's empty. You don't like it? It gets worse. Let's say you have a Catholic family that's infinitely big, okay? And you come into the Catholic and you say, I want a room for all my kids. And they say, well, we're full, but it's okay, we can fit you in. You say, how? He says, well, I'm going to move the person from room number 1 into room number 2, room number 2 into room number 4, room number 3 into room number 6, and so on. And what happens is all the odd number of rooms become free. And there are an infinite number of odd numbers, so that's fine. It could fit your family. So you see, the problem with infinity is you can do almost anything with it. And almost anything you come up with is nonsensical. And this is a problem. And so physicists came up with a solution. And here's where Mr. Higgs came around. And it's amazing. This is true. So we have this theory that the weak force must be explained by exchange of a massive particle, but the theory doesn't work. And what Mr. Higgs realized, and a few others, is that just like I can tell the difference between left and right in this room, just because it's an accident of this room, there are different sets of people here than there, maybe there are other things that are just an accident of our existence. For example, I live in Phoenix now, so I don't see this very often, but if you're on I grew up in Canada and I used to see it a lot. If you're in a window in the winter time and you see icicles grow, they form these beautiful patterns. Now, no one thinks there's any preferred direction in nature, that laws of electricity and magnetism are different in different directions. But if I happen to be a microscopic being living on one of these icicles, then that direction would be very different than those directions. Because all the forces of the atoms would line up, and I would suddenly see that electricity behaved differently in one direction than another. And I might infer that there was something different about electricity in this direction and that direction. Or I might be a physicist, and I might say that's just an accident of my existence. I'm living on an icicle. And so what Mr. Higgs and others suggested is that our existence is the same kind of accident. I think hopefully, yeah, I'll do this. It's the same kind of accident. Maybe mass itself is just an accident of our existence. So maybe, and how can I explain this? Well, maybe like the icicle, I live in some background that distinguishes things that appear to be different but are really the same. So let's say there's a uniform background field throughout the entire universe that I can't see. And all particles interact with that field, but interact with it differently. So photons don't interact with it at all. But other particles interact with it and experience resistance. And by experiencing that resistance, they seem more massive. You know, if your car breaks down on the highway, you roll it, you can push it until it hits the dirt, and then it suddenly can't be pushed. It suddenly feels heavier. Or if you try and swim through water, you won't feel anywhere near as heavy as if you try and swim through molasses. So maybe we're all swimming through molasses. Maybe the elementary particles in nature that we measure as having mass only have mass because they interact with that field. And some of them are more massive because they interact more strongly with that field. And some of them are less massive because they interact less strongly with that field. So mass itself is an accident of our existence. And maybe that's why I can understand that fundamentally the weak force is the same as the electromagnetic force. That this is the Feynman diagram for the exchange of a photon causing electromagnetic force. And maybe there are these diagrams that demonstrate the weak force. And maybe this particle, we call it the W particle, the Z particle, is really massless in the fundamental theory. So in the fundamental theory it's massless, and just like the photon, the mathematics works out, you don't get infinities. But this W particle actually interacts with this background field and therefore appears to be massive. It gets a mass because it interacts with that field, and that's why it behaves differently. Now think about this. This is an amazing intellectual house of cards, built up over 100 years from Maxwell and Faraday through Einstein and Feynman and Fermi, saying, look, we have this, everything works, but it'll only work if somehow mass is an accident. Now, this is an amazing story. It all holds together and the mathematics work out really nicely. And in fact, it was put together in a well-defined way by these guys here who used Higgs's idea to apply to the electromagnetic field. Steve Weinberg, Shelley Glashow, and Abdus Salam, who won the Nobel Prize in 1979 for unifying electricity and magnetism and the weak force. Saying that if this was the case, these two fundamental forces in nature, which seem so different, could really be manifestations of exactly the same thing. Yet another unification of the type that was first started by Maxwell and Faraday in electricity and magnetism, and Einstein in space and time, and now a unification of the weak and electromagnetic force. And all the mathematics worked out. The people who showed the mathematics worked out. These are two other pals of mine won the Nobel Prize in 1999 for showing the mathematics worked out. And then the mathematics was so beautiful, it was shown that it could be applied to the other force in nature called the strong force, and three other friends of mine won the Nobel Prize for explaining that. Everything works with this amazingly beautiful story, but science isn't a story. That's what's important. This beautiful standard model had been developed by 1974. I remind you, in 1960 we understood one of the four forces in nature. By 1974, we understood three of the four forces in nature as quantum theories: the electromagnetism, the weak force, and the strong force. And every single experiment that we ever did could be understood by this one beautiful mathematical framework, this one beautiful unification. Everything worked. And we even got more fancy. We said, if we got this, we can do a lot more. And physicists start talking about grand unified theories and all sorts of neat things. But you notice, up to this point, there's a problem. Physics isn't just a story. If it were, it'd be religion. It's a story that makes predictions that can be tested. And as beautiful as this incredible idea of this invisible field was, it's invisible. like God. And just because it's invisible doesn't mean it exists. Okay? So if this idea worked, then you have to be able to test that idea that there's an invisible force. So the Higgs field had not been measured. So we go back to the earlier sex talk. Forget spanking each other. Physicists want to do the ultimate sadomasochistic act. We want to spank the vacuum. Because the laws of quantum mechanics tell us that with every field is associated a particle. And if I spank the vacuum hard enough at a given point, I'll produce particles. So if this invisible Higgs field exists, if I can make a machine that will spank empty space hard enough in a small enough region, I'll produce real particles, which we call Higgs particles. And I could draw Feynman diagrams that'll explain how to produce them. I'll take particles inside protons and smack them together. And if I smack them together, I'll produce these real particles. And we could use the physics to calculate how frequently they'd be produced and where you might look for them and what the signatures are. I won't go into any of this. So that we could predict that. But then you have to build a machine to do it. And so we tried in Texas. In Waxahachie, Texas. For anyone from Texas? Okay. I used to visit Waxahachie all the time in the late 80s and early 90s because we were building the world's greatest machine there. Okay? Many of you know that we dug a tunnel 60 miles around. The largest tunnel ever dug by humanity to build the largest accelerator that was ever going to be built at that time, called the Superconducting Super Collider. It got canceled by Congress in their wisdom because it cost too much. It cost $10 billion, which is the air conditioning bill in Iraq for one day. Okay? So we didn't build it there. But the Europeans had a tunnel that already existed. It was 26 kilometers around. And they decided to build a machine we call the Large Hadron Collider. And it is the most amazing machine that's ever been built. It is a 26-kilometer long machine. You can barely see the curvature of it. Moving elementary particles, protons, at 99.99999% the speed of light in this direction, and other protons at 99.99999% the speed of light in this direction, around and smashing them together with enough energy, we hoped, to produce the Higgs particle. In order to do that, we had to guide them with magnets. But regular magnets aren't strong enough, so we had to have superconducting magnets, which means we had to build a superconductor 26 kilometers around, with 5 tons of liquid helium that would cool this down. 10,000 magnets. Built, by the way, underneath the ground in Geneva. If you go to Geneva, you won't even know it's there. In fact, the picture is here. Here's the airport of Geneva. If you ever land there, you're right on the edge of the Large Hadron Collider. It's right underneath you. And these particles go around and they cross the border into France without passports at about 10,000 times a second, in that direction and that direction. And then they collide together. And we predicted that maybe, just maybe, when two protons collided together with the kind of interaction strengths we calculated, you might produce this new particle, the Higgs particle. In the process, of course, there are about 10,000 other particles produced, 1,000,000 times a second. These were the simulations, and on July 4th, a wonderful day, 2012, those simulations turned out to be true. In the detectors were exactly the particles. 50 events had been seen, and we weren't certain it was a Higgs particle, but if it looked like a Higgs particle, and it kind of had the properties of a Higgs particle, and it walked like a duck and it quacked like a duck, we kind of thought it was a Higgs particle. We didn't say it was, because it only had a 99.99% chance of being a Higgs particle. That's not good enough. Within 6 months, however, we had enough experimental results that it now had a 99.99999% of being a Higgs particle, had all the properties that are predicted of the Higgs particle, and we've discovered the Higgs particle. This incredible intellectual journey began late at night on pieces of paper, and as a theoretical physicist, I have to tell you how scary it is to be sitting there working on a piece of paper to think that maybe nature obeys this crazy idea you have. It is intimidating, and every time it happens and you're right. I remember when I first argued there was dark energy in the universe and it turned out to be true, I said the first time I didn't believe it was when they measured it. Because it just seems too crazy that we can actually peer into the mind of nature, not the mind of God, but into the natural world, seeing that hidden reality that's so far from our everyday experience and be right about it. And this intellectual edifice, which is truly the greatest bit of intellectual activity that humans have ever endeavored upon, is true. And it's not just a theoretical framework. There's more, because the greatest thing about science is it's not finding the answers, it's the questions. And the minute we discover the Higgs, there are lots more questions we have. It's like an impressionist painting. It looks great from far away. When you get close, it looks pretty shitty. Okay? And when you start to ask, well, that's great, but why does the Higgs have the mass it does? We don't know. Why is the weak force so much weaker than the electric force? Why are there four forces in nature? Well, I could go in and I'm not going to, it turns out there are reasons to think about this, but I want to get to the question period, and I explained some things I wasn't planning to explain, so I think I'll skip this slide. And I'll skip supersymmetry because God knows who cares about supersymmetry. Yeah, and well, the point is, what we're thinking is that answering all of those fundamental questions will mean that there's a host of new particles we're going to discover at the Large Hadron Collider when it turns on in 2 years. In fact, most of us thought we discovered those new particles before we discovered the Higgs. I didn't actually even believe the Higgs existed. It just seemed too slimy an explanation. Too simple. Nature would surprise us. Because in my experience, every time we turn on something new, we're surprised. So nature, the imagination of nature is much greater than our own. And I thought it just seemed too simple an explanation that there's this invisible field. It must be something trickier. In this case, we were right. If it's not there, if there's no other particles, we won't have the answers to those questions. And that's a problem. Because, you know, when physicists just start thinking and not doing experiments, like we did for the last 40 years while we're waiting for the Large Hadron Collider, it's like people know sensory deprivation tanks. Begin to hallucinate. You invent string theory. You do all sorts of stuff. And maybe we're at the edge of knowledge. This may be the end. We don't know. Because I'm telling you one thing for certain. If we don't discover anything else, then it tells us that the answer is somewhere else. But we're not going to go to politicians and say, guess what? We didn't see anything. Give us a new accelerator. But I want to close, literally, by saying that this is the example, not just this intellectual story, but why science is so wonderful and why it's not like religion. Because it truly binds together humanity. To build the superconducting, the Large Hadron Collider, you had thousands of physicists, 10,000 physicists, from over 100 different countries, speaking dozens of different languages, having dozens of different religions, some of them, all working together to build a machine that worked at the level of a millionth of an inch. And the requirements of that machine were amazing. These machines are like the Gothic cathedrals of the 21st century. They are the epitome of the beauty that technology and culture can bring together, and their humanity at its best. Truly beautiful. The requirements are amazing. Here's one of the detectors at the Large Hadron Collider, just a detector. Here's another one called the compact muon solenoid, which has more metal in it than the Eiffel Tower. I think there's a really good picture. There's a much better picture of it. These machines are meant to be able to measure things that are remarkable. For example, oh yeah, that's what I wanted to get. Every second at the Large Hadron Collider, every second enough data is generated to fill more than 1,001 terabyte hard drives. More than the information in all the world's libraries every second at the Large Hadron Collider. In order to build that machine, took new technology. In order to understand how to analyze that much data, has required us to build new types of computers. Of course, that technology is going to feed back into your lives. Just like the World Wide Web was developed at Geneva, at CERN, for the previous machine. The net that you use every day was developed because 1,000 physicists working on a machine they wanted to be able to communicate to each other without knowing where they were. So they built a technology, the web, that would allow you to store information when it wouldn't matter where it was. You wouldn't know where the information was. You could access it. That's how your lives have changed. But we have built that to ask one of the most esoteric questions in nature. In the process, finding more about our origins. Because the last thing I want to say is that this tells us if the Higgs field is really there, as the universe evolved, it's an accident, a cosmic accident. And I want to end on beer because we're going to have some, and also because I'm Canadian, and because it really is the case. I want to. Some of you may have had this experience. So you have a party, and you get beer, but you forget to put it in the fridge. And you realize an hour before the party, so you put it in the freezer. Does it happen to some of you, maybe? But then you forget during the party that it's in the freezer. And then after the party, you remember, you open the beer bottle, crash! What's happened? Because the beer was liquid under high pressure. But when I open the top of the beer bottle, of course, it freezes automatically and breaks the glass. Lots of energy was released because it's undergone what's called a phase transition, going from liquid to solid. And if this picture of the Higgs is true, which we now know it is, as the universe cooled down in the early history of the universe, what have ultimately happened is it froze and a Higgs field formed. And it didn't have to be that way. Under different conditions, changing the conditions very slightly, that Higgs field would never have formed. But if that Higgs field would never have formed, then all particles would be massless, and we wouldn't be here. So that simple accident of a phase transition in the early universe produced a universe in which we can live. There was no purpose to it, any more than there's a purpose to the beer bottle breaking when you open it up. It's an accident of nature. And that's the accident that I want to celebrate. That I found that we are like living on an icicle. Or we are like those people back in Plato's Republic, staring at that wall, and through the progress of science, empirical inquiry, skepticism, and experimental testing, we have been able to learn about this hidden universe that is so remarkable. And so we are, as we wait for the Large Hadron Collider to turn on again, just like this young lady, opening the doors to the next hidden universe, and this great story of a real universe, which is so much more fascinating than a universe of myth and superstition, a universe written down in a book by Iron Age peasants who didn't even know the Earth orbited the sun, cannot compare to the real universe. Thank you very much. Thank you. Last question, then. Thank you, thank you. You're very patient. Thank you. It's been a long day. I will take some questions. I don't think I had anything after this. Yeah.
I believe.
Oh, my. Okay, yeah, we'll take some questions. Are you going to field them or should I?
Are they going to fight each other?
What?
I think these two are going to fight the microphones.
Oh, okay, yeah. That's right. That's why you should shut up and I'll continue to talk. Okay. Okay. No, I'm sorry. Oh, it works. Okay, so let's have some questions, if there are any. And I realize I'm all that's standing between you and dinner and then partying later, and book signing. And by the way, I'll be happy to sign things if you don't have books. And I certainly am going to be here through tomorrow, so I'm not running away. I'll be able to answer any of your questions, even if they aren't here. Let's start there. Yes, you.
Okay, I wrote this down.
Okay.
Your talk alluded to advanced practice of philosophers. And I know you've had a lot to say in the last year or so about metaphysics. I've been reading your book and a naturalistic metaphysics book at the same time. Metaphysics naturalized. Everything from the scope by the human rock.
It sounds like a tautology, metaphysics naturalized, but anyway, yeah.
Okay, but Ross was at the naturalism over competition.
Is this Hugh Ross? Oh, he's a crackpot. Let's not talk about him. Okay.
So this sounds that the naturalism
Okay.
with Weinberg and
Okay.
and in their book they argue for approach to metaphysics that forget our intuitions, philosophy.
Yeah.
Our intuitions are useless. What we should really be doing is trying to look at what are the things that science points to that are determinants.
That are what?
What are the options that are available to us that science points to but are underdetermined at this time? So I'm going to ask you what you thought about that.
Well, I think of that as theoretical physics. I mean, what I do, if at my best, if I'm lucky, is try and say, you know, what we know and what is implied about what might we know, what might be true, what are the possibilities. I said that in my Star Trek book. That's why Star Trek is fascinating, because it was about the possibilities of the universe. And to me, that's what motivates me, and it motivates all my colleagues. I don't care what's practical. My ex-wife used to be upset by that. I care what's possible. And so that's the joy that I have. I get to think of all sorts of possible universes. But what's really important to realize is that most of those universes are wrong. In fact, almost all the time they're wrong. The one thing we don't explain enough is that almost all scientific ideas are wrong. Okay? If it weren't, anyone could do it. Okay? We can't just say it's beautiful and therefore it's true. In fact, I ended one of my books about extra dimensions with a quote from Hermann Weyl, who's a mathematical physicist, who said, he was a mathematician primarily. He said, in my work, I'm often forced to choose between truth and beauty. And whenever I do, I always choose beauty. That's because he was a mathematician. We have to choose truth. And the only way to find the truth is not to get revelation or to think of it or decide what's logical, which is one of the problems I have about classical logic in the case of the classical philosophers. None of that matters. What makes common sense doesn't matter. It's what the universe tells us is true, and the only way to find that out is by experiment. That's the way we find out what's true. All the way in the back there. Yep. Yep, you.
Your talk today presented 3 of the 4 forces. Where are we on gravity right now?
Okay, well, very astute of you. Well, that's the point. We understand 3 of the 4 forces in nature, and I could have gone through grand unification to explain how they might relate, but we don't understand gravity. We don't have a theory of gravity that is consistent with quantum mechanics. In fact, what is interesting is that the mathematical theory of gravity has exactly the same form as the mathematical theory of the other 3 forces in nature. They're called the gauge theories. So the mathematics is beautiful, but when you put it in the form of gravity, it just doesn't work. And so we're flailing around. And it's true that string theory was, to be fair, the best proposal so far for a quantum theory of gravity. It just hasn't gone anywhere. Okay, it hasn't done anything. In fact, we don't even know what the theory is. Seriously. And what offended me about it, and why I make jokes about it, is because people called it a theory of everything. Well, in some sense, if it was, it would unify gravity and the other forces in nature, and make it seem like we understood everything. But of course, as my friend Frank Wilczek, who was one of the Nobel Prize winners on the slide, said, it's really a theory of almost nothing. Because the reason we don't have a theory of quantum gravity is the scale where gravity and quantum mechanics become important is a scale that's 18 orders of magnitude smaller than the scale we're measuring at the Large Hadron Collider. And therefore, it is almost impossible to imagine experiments which could test that. Although it's not impossible, it's almost impossible. And some of us have, tried to do some ideas that might propose such experiments. But therefore, that's why, even if you have a good theory, to test it, which is the heart of science, becomes very difficult. And so it's not too surprising, perhaps, that we don't have a theory of quantum gravity. I also suspect, as I did with the Higgs, that all the current ideas we have are wrong. That's just my experience as a scientist. And I think, fortunately or unfortunately, to have a quantum theory of gravity, we may just require a good idea, which is a hell of a lot harder to come up with than a good experiment. And so wait and see. Maybe one of the young people in this room will have the good idea. Yeah?
So I've run into a couple of people over the past year or so that have bought into this strange worldview, which is kind of like a marriage between ideas from solipsism and strange interpretations of quantum physics.
Oh,
yeah,
this new age quantum crap.
What
Yeah.
the bleep do we know? And Deepak
Yeah, what the bleep do you know in Deepak, yeah. I gave him a prize. When I used to write a column for Scientific American, I gave a prize to the biggest abusers of science. And So yes, the problem with quantum mechanics is because it's so weird, con artists can use it. And it is, of all of science, it's the only area of science where I know that con artists make money from, well, nowadays, from abusing things. I could tell you their stories, but I won't. So the idea is that quantum mechanics tells us that the universe at a very small scale is strange. Stranger than you can imagine. Like an electron can be in many different places at once. And as I told you, all sorts of weird things can happen if you can't measure them. You know, an electron can be doing many things at the same time. And even weirder, if I observe an electron, it'll behave differently than, if I observe an electron, I can say it did something, but I can't say it was doing that stuff if I hadn't measured it. In fact, I can say it wasn't. It was doing everything at the same time. It was going, I measure an electron going from here to the back of the room. I measure it, see it going there, fine. But if I hadn't measured it, if I measured it here and then again at the back of the room, I couldn't say it took the path it took if I'd measured it. In fact, it didn't. It took a path to the moon and back. It did all sorts of other things all at the same time. So what it sounds like it's saying is that things behave differently if you observe them or if you don't. That seems to suggest to some people that human consciousness is important. And what these con artists say is, quantum mechanics says, if I want it, it will happen. You know, it's the secret. If you, in that book, The Secret. If you can affect the outside world by thinking about it, because the world behaves differently if you observe it. But it's got nothing to do with consciousness. And quantum mechanics definitely says if you don't do an experiment on something else, if you don't physically do something to it, then you don't affect it. Okay? Consciousness has nothing to do with it. An electron being measured by an unconscious machine behaves differently. There's nothing to do. Humans and human consciousness aren't a part of it. And moreover, you only affect those things you measure. So even though quantum mechanics is still really strange, and I'll give you an example of how strange it is, just so lest you think it's reasonable. It's the basis of quantum computing and something called quantum teleportation. Okay? It is a true fact that if I carefully prepare an initial state of, say, 2 electrons in a very carefully prepared quantum mechanical state, with one spinning one direction and one spinning another, and I let them separate, and I enforce that they don't interact with their environment, and one goes to Alpha Centauri and one is here. I measure this electron here, and I measure it to be spinning in a certain direction. Instantaneously, that particle there we know is spinning in the opposite direction, whereas before they were spinning in all possible directions. Now it sounds like there's communication faster than light. There isn't. It's just because you think about it wrong. There's no way you could use that to ever send a message from here to Alpha Centauri faster than light. And I've already gone on too long, so I'm not going to explain it to you, but I'll be happy to later. But it's weird. It's this spooky action at a distance that Einstein hated so much. But it's only spooky because Einstein didn't believe in quantum mechanics. It's only spooky because we insist that our classical worldview is sensible. That we have to have an interpretation of quantum mechanics. But as my late friend Sidney Coleman, who's a professor at Harvard, used to say, we should talk about the interpretation of classical mechanics. Because the world we see is just a classical approximation of the real world. And therefore, we shouldn't expect, we're seeing the shadow of reality. We shouldn't expect the shadows to behave sensibly. It's the underlying reality. And if our sense of common sense, and if you watch our new movie, you'll see Richard and I are having a discussion in Australia, and he points out that common sense arose because we developed them in Africa to avoid lions, not to understand quantum mechanics. So if our common sense is violated, it's only a property of the fact that we're classical beings. And we shouldn't be offended if our common sense is violated, because it's got nothing to do with the underlying reality. Too long, but that's it. I'll take 2 more questions. Is that okay? Is that going to be good? You look related to someone important. Okay.
I look familiar, but I'm actually Will's antimatter.
Oh, okay. Okay.
So my question pertains to, I know that mathematics and logic would be vital to this, but in the absence of experimental capabilities at the moment, how do theoretical physicists peer review one another? What are they looking for?
Well, the first thing you're looking for is mathematical consistency. The question was, how do we peer review one another in advance of an experiment? So you may have an idea, and the first thing is it mathematically consistent? Second thing is it maybe testable? Okay? And is it interesting? Does it pertain to something that, that might in principle be measurable. Okay? So that's what determines whether things get published at the forefront of theoretical science. Before you can test things, it's just consistency, logic, interest, and potential testability. And that's why most of the stuff in the scientific literature is wrong. Most of the theoretical papers I've written in my life are wrong. Because the ones that have not tried to explain things that have happened, but tried to predict things in the future. Because nature hasn't been wise enough to follow my advice. You know, it's just the way it is. And by the way, let me make it even clearer, because when some of you may debate creationists, young earthers, and etc., and they will point out, I remember well before Zach was doing his noble work, I've spent many years, starting in Ohio and Kansas and New Orleans and Florida, going around trying to defend the teaching of evolution. And one of the first places we did it was in the New York Times, was a debate in Ohio with some of these intelligent design idiots from the Discovery Institute. Stephen Myers has just written a new book, and he's the slummiest of the bunch. And they pointed out they had a paper published in the peer-reviewed literature. And I point out, doesn't matter. Being published doesn't mean anything. Just lots of crap gets published. Even stuff that's wrong gets through the referees. Being published doesn't matter. But if it gets published and it's interesting, and then someone else takes it up and they do experiments testing it, and the idea works, then it begins to be in the canon of science. So the way we do things in science is you have an idea, if you're lucky, and then you test it and you see if the idea is right, and then other people test it and it begins to get done, and eventually 30 years later it gets into the high school curriculum. Okay? But what the ID people want to do is they just want to avoid all those intermediate steps. You have an idea and just put it right in the curriculum. Let's test it in the high schools, not on all the other places. And that's what's so stupid about the whole thing. I'll take two more because he was kind of a shill. Yeah?
Easy one. When and where is The Unbelievers going to be available here?
When is The Unbelievers going to be... have you seen the trailer? I have the trailer. Anyway, I show it to you if you want to see it. It's a great movie. I'm very excited about it. Yeah, we just had, as was pointed out, a premiere at a film festival in Toronto in April, end of March, beginning of April. End of April, beginning of May. And we are currently, I just flew from Australia and stopped in LA on the way here to negotiate with Hollywood people, which is weird. And we are, by early July, we will know the distribution arrangements. And it should be, we are aiming, our goal is to have it in theaters. We could put it directly to DVD, but our goal is not to preach to the converted, but to get it in theaters, and we think it's likely, and we have a number of possibilities here. I can tell you that if you want to go to Australia, the Australian premiere will be November 2nd at the Sydney Opera House, and we will be doing this year, we expect, showings in New York and LA, but elsewhere. But we're going to try and win an Academy Award for it. So we have to have a week of showing in New York and LA for that. So stay tuned and go to the Unbelievers website, and we'll keep people. I get 100 emails a day asking when it's going to come, and I wish it was out, but we're trying to make sure it gets in theaters. So and it will, after that, we promise, get into iTunes and Netflix and DVD and all the rest. Okay, but it is a rock and roll tour film about science, and and it has a number of and some people have criticized, I don't know if we all know about it, but a number of my friends who are celebrities are in it. So Woody Allen and Cameron Diaz and Bill Pullman and Ricky Gervais and a few others, and I'm very excited about that. Some people have criticized us for that, but to me, the virtue of all this is that you shouldn't. These are people who people don't associate as being interested in science. But there are people who in this movie point out that science is necessary to understand the world. And for me, that's the real, it'll bring people in who know of Cameron, but don't know, the one or two people who don't know who Richard and I are. You know, it'll make them realize that it's okay to be interested in science, even if you're not a scientist. That's the point. Everyone, as I think Zach was saying earlier, everyone should be interested in science because it's an essential part of our culture. Anyway, last question. Who has the best question? I'm going to take a woman, sorry. Okay. Yeah.
This is kind of fun, I guess. What is your thought on the possibility of
Oh, okay. Well, it is fun. I could go. Time travel is fascinating. I did write a lot of it. It's like when you get to be my age, I can always say it's in my book, like O.J. Simpson used to say. But I wrote a book called The Physics of Star Trek where I talked a lot about it. And the interesting thing is, when I wrote that book, it caused a big stir because my friend Stephen Hawking wrote the foreword for that book. And in the foreword, he says that, as I say in the book, that time travel may be possible given the laws of physics. And previously, he'd said it was impossible. And the London Times produced a front page spread saying Stephen Hawking changes his mind in this book. He'd previously given the argument that if time travel were possible, we'd already be inundated by tourists from the future. And I countered him by saying that they all went back to the 1960s and no one noticed, so he had to change his mind. But the point is, what's fascinating is that Einstein, with both special relativity and general relativity, connected space and time. And you can easily do a circle in space. We do it all the time. Okay? And if space and time are related, the question is, can you do a circle in time? Can you go backwards in time? And that's a fascinating question. We're all going forwards in time. Right now we're time traveling. And Einstein showed us that time is relative, so that people are going forwards in time at different rate depending upon their state of motion. In fact, my clock is taking it at a different rate than yours because I'm higher up. Because gravity. And it's not esoteric. As I wrote in a piece, I think, for the LA Times and the New York Times years ago, your GPS would stop working in about 2 seconds if we didn't take into account the clocks ticking at different rates due to general relativity. So it's not esoteric, it's essential. But the question is, can you go back in time? And the answer is, in principle, yes. General relativity allows it. It says that you can create a space and a time that behave however you want if you have the right conditions of energy. Because space responds to energy. So you create the right conditions of energy and you can create time travel. But the unknown question is, can you create those conditions of energy? Or do the laws of nature forbid you creating those conditions of energy? And many people would say they do because of a version of what Hawking said. Because of paradoxes. If time travel is possible, there are tons of paradoxes. My favorite being the grandmother paradox, as I called it. So you go back in time and you kill your grandmother before your mother was born. That's fine, but then your mother was never born, but then you were never born. So how did you go back in time and kill your grandmother? Gives you a headache. Gives physicists headaches. And so that's why many physicists have said time travel must be impossible. But, and this is a good way to end, as I've often said, the universe doesn't give a damn what you think about. Okay? And what a damn what you like. And it may be that time travel is possible, and then we'll just have to find a way to understand how such a crazy universe can make sense. That's what we did in the 20th century with relativity and quantum mechanics. That doesn't mean time travel is possible. But just not liking the idea is not good enough. We have to test it. Thank you very much. Thank you very much. You're too kind.